I want to talk about scientific integrity, and there is a problem, and it's not just in climate science, but across the sciences where self-correction doesn't work as well as it should. One thing that makes science science is that it is self-correcting, and I have a few throat-clearing quotes here to start with. Carl Sagan, "It's okay to be wrong." In science, that's how it works. We put ideas out there, we test them, people criticize them. Good ideas carry on, and the bad ones don't. Um, a second point is from the U.S. National Academy of Sciences. Researchers have a fundamental obligation to their colleagues, to the public, to themselves to ensure the integrity of research data. And that's kind of a theme that cuts across the cases I'm going to share with you today. A little more throat clearing. Here's some assertions that I'm not going to be talking about. Human-caused climate change is real and it poses risks. Effective mitigation and adaptation policies make good sense. Scientific integrity is essential for science to work. The importance of climate change does not justify compromising scientific integrity, as some people will say. And importantly, this is not a talk about climate change, and it's not a talk about climate policy. This is a talk about scientific integrity that involves examples from climate science research. With all that, I'm gonna walk through three cases that I have published recently and extensively on, where I see there have been some significant failures of integrity in climate related work. And I'm going to go from the less important to the very important as I go through these three cases. So the first one is the ICAT data set, and I put data set in scare quotes for reasons that you will understand momentarily. So here's me, 1995 at the National Center for Atmospheric Research on the right. And on the left is my colleague, Chris Landsea, who at the time was a postdoc with William Gray up the road from here at Colorado State University. He would come down to NCAR, where fantastically there was a basketball court out back where we would play, and we talked about hurricanes and our related work there. And we discovered a puzzle. He had just published a paper that showed that the period 1991 through 1994 was the quietest 4-year period for North Atlantic hurricane activity. And I had just published a paper that showed that the same period was the most costly period. And so we were discussing how do we make sense of damage trends in the context of climate trends.
Yeah.
Excuse me. If you just look at inflation-adjusted U.S. hurricane damage, this is just an example chart. You see this sharp increase, obviously, even in the 1990s, people would look at economic data like this and say, "Aha, we see a signal of human-caused climate change." Obviously, things are much more complicated. The two panels at the top show continental U.S. landfalling hurricane trends. Hurricanes on the left, major hurricanes on the right. You don't have to be a statistician to see that there's no trend over that 120-year period. However, what is changing is the population in coastal counties, and importantly, how much wealth people have accumulated. So it's not just climate that affects damage, it's obviously what society does also. So we published a series of studies. This is from our 2005 or 2008 study that went through 2005. The graph there shows what we estimate historical damages would be if every hurricane were to make landfall in the same year. So in this case, this was 2024 version. And we see a lack of trend that mirrors the lack of trend in landfalling storms. So that's good. So let me go back in time. After this paper on the right here was published in 2008, there was a local insurance company. It was actually housed in the office park of the University of Colorado. I was close with the CEO, who's now moved on and retired. And we thought, well, wouldn't it be interesting to try to bring our normalized hurricane loss data set to the insurance industry? I had a fantastic student named Joel Gratz. He got hired on at ICAT. And with my support, they decided to create what's called the ICAT damage estimator. It was a really neat little tool. You could take any hurricane that was currently active in the basin and plot it on this map and show every storm historically that was within 50 miles or 100 miles of its position, and then see where did those storms go on to make landfall and how much normalized damage did they cause. So it was a way for people in the industry to get access to our data set and put it into a real-time context. I just have this silly little screenshot. ICAT was sold. CEO made a pile of money. He left. My former student, Joel, he moved on, started his own company, super successful now in Colorado. And I lost touch with whoever took over the company. And I just assumed that that neat little tool we created, the damage estimator, didn't exist anymore. Well, I was wrong. So meantime, I continued work with colleagues to keep updating our normalized hurricane damage data set. This is the 2018 version, led by my former student, Jessica Wenkel. And you know, we're actually have a draft of the next version sitting on my desktop right now. This is the 2018 version, and it's Wenkel et al. You'll see that name come up in the next few slides. But that's just the most recent version of the data set that we used. All right, so 2019. This paper gets published in the Proceedings of the National Academy of Sciences. Normalized U.S. hurricane damage estimates using area of total destruction. All right, that's good. I'm always excited to see people trying to build on and extend our work. This paper, Grinstead et al., they had found a revised version of the old ICAT data set online. And they used it to publish a study with results that they claimed contradicted our results. They had no idea that the quote unquote data set they had found on the internet originated in our work. Interestingly, if you go to their supplemental information, they publish this graph, which shows that's just a comparison between what they call the Wenkel et al. Data set and the ICAT data set. Well, they're about 90% similar because the ICAT data set was originally based on ours. But puzzlingly, if you can look at the far right, you see all those dots below the unitary line. That indicates that the ICAT data set, scare quotes, had higher values than the Wenkel data set. And there was a whole bunch of other changes there also. I did some sleuthing, helped by their description of what they did. The base damage estimates, so these are the original estimates before we apply the normalization technique. They said that they were compiled by us, yes, and updated by ICAT. And so when I worked with ICAT, they were expected to use our data as it was, not to update it, not to change it. And they say we use the ICAT data set for the base damage record. So one thing that was done after I moved on from ICAT is the interns who were updating that data set simply stapled onto the end and replaced some of our numbers from the NOAA billion-dollar disasters data set. That's why the losses are much greater. And so if we take a look, here's the base damage. So on the left is the Grinstead ICAT estimate, and on the right is Wenkel, what we did. So for the period 1900 to 1926, they're identical. Way back in time, they're the same. But if you look more recently, the base damage from Grinstead and ICAT is much larger than the estimates we used. There are reasons for that, and the reason for that is the methodology of the billion-dollar disasters was to take everything, including the kitchen sink, and throw it in to create very large loss estimates. We struggled mightily to have apples to apples comparison of the data over time. The National Hurricane Center had a very simplistic but consistent approach to damage estimation that we applied. So their finding of an increase in hurricane losses after normalization simply results from what's called this Frankenstein data set. They stapled onto the end of it some values that were apples compared to the oranges of the earlier years. So by the time the IPCC AR6 was written, there were more than 60 normalization studies in the peer-reviewed literature. I published a review. I think 9 of them were of U.S. hurricanes, but from all over the world for all sorts of phenomena, floods in China. You had landslides in Switzerland, all sorts of studies. Only one of these 60 plus normalization studies claimed to have attributed disaster losses to human-caused climate change. That was Grinstead et al. The IPCC ignored this entire literature and featured Grinstead, which is a fatally flawed study. So this is just a tabular representation of my literature review. All of these studies, except the one highlighted in yellow, Grinstead, did not claim to have attributed any detected trends, of which there weren't many, to human-caused climate change. So it's a pretty blatant example of cherry picking by the IPCC, which I've written about. All right, let's go to the U.S. Fifth National Climate Assessment. They have this sentence in there. After accounting for changes in the value of property and other assets placed in harm's way, that's the definition of normalization, hurricane damage in the United States has generally increased since 1900. And the citation goes to our friend Grinstead in the fatally flawed paper. What the U.S. National Climate Assessment did not do is acknowledge the 9 other studies that have been published on normalizing hurricane losses. We do some of them, but others have also. None of these other studies found an increase in hurricane damage. Here's Grinstead. So maybe you might think, well, maybe Grinstead is just the cream of the crop. It's the best study out there, and we can dismiss all these. After all, it's been cited 122 times, which is respectable out in the literature. Here's the citations for all of these other studies that were ignored. So there's about 30 times more citations to other literature that was ignored. So I wrote on this. I contacted Kerry Emanuel, who was the editor at PNAS. PNAS refused to retract this paper. They investigated. They said everything was just fine. You probably won't find a more blatant example of misuse of data than this. Well, until the next study. All right, then last year, another study was published by Hugh Willoughby and colleagues using another version of the ICAT data set that they had found online. And they were very clear about what they were trying to do. This paper seeks to verify or refute the idea that anthropogenic global warming has no effect on normalized tropical cyclone damage. So let's set aside the futility of trying to prove a negative. And Hugh Willoughby was very explicit in emails with the editor and me as I called this to their attention. They were trying to undercut our work, and there were overt claims of perhaps we engaged in some sort of research fraud because the ICAT data, which was obviously the gold standard, disagreed with the data we used with Winkle et al. So at this point, I decided, all right, I'm going to have to dive into this again. And so I wrote a paper, and it was just recently published on this data set. So I took the Willoughby study. Each one of these bars represents a year's worth of hurricane data. If the data is identical between the Winkle data, our data, and the version of ICAT that Willoughby used, then it's a +1. And if it was changed, it's a -1. And so what you can see is that most of the changes are indeed after 1980, although puzzlingly, there were some changes earlier. And we can also look at the direction of the change. So again, +1 means that they increase losses as compared to our data set, and below -1, they decreased. So very few decreases. Again, puzzling. We have no idea why. There's no metadata or origins of where the data came from. But what you can see is that in this period after 1980, there are significant increases. So what I did is I simply just plotted the base damage, the ratio between the data sets. And then I stuck a trend line through it. So before any normalization is done, you can see that the data set has an increasing trend. That's because they stapled on some version of the NOAA billion-dollar disasters data set onto our data. And so the results of both Grinstead and Willoughby are 100% undeniably the result of a Frankenstein data set, nothing to do with behavior of hurricanes. So I asked this editor of Journal of Applied Meteorology and Climate to retract this paper for the obvious reason it was using a flawed data set. They refused, but they said, you can write a comment on it. So this is how I concluded my paper. I didn't pull any punches. The original data site hosting the flawed data set is gone, but it lives on through these papers in the peer-reviewed literature. And Grinstead has been featured by IPCC in the National Climate Assessment. The errors are so obvious and significant that the editorial boards from both journals should retract the papers to prevent this from persisting in the literature. And I said this is an opportunity to uphold the fundamental obligation referred to by the National Academy of Sciences by correcting course. They didn't. All right, that takes us to the billion-dollar disasters. So in parallel with discovering the flaws in the ICAT dataset, I started taking a deep look at the billion-dollar disasters dataset by NOAA, National Oceanic and Atmospheric Administration. I first started writing about that about 2010. At that time, the billion-dollar disaster tabulation, it's not really a dataset, tabulation was put together by a couple well-meaning climate guys in Asheville, mainly as PR to show that there's a lot of disasters, so you might as well support NOAA. At the time, they didn't even adjust for inflation. I pointed that out, and NOAA made some changes. But over time, that went from a PR press release sort of thing to a rigorous scientific data set, and nothing had changed. So I wrote a paper, and it got published in a Nature journal, Scientific Integrity and U.S. Billion-Dollar Disasters. I applied the criteria of NOAA's own scientific integrity policy and the U.S. government's guidelines for information quality. Without getting into all the gory technical bureaucratic details, this tabulation did not meet many of the standards required of a data set to be used as significant scientific information in support of policy. It's colorful, it gets a lot of press, but it wasn't scientific quality. And I'll just go through a few examples. Ownership of the data set changed hands around 2008, and at that time, the counts of billion-dollar disasters started increasing dramatically. One reason for that was a roll-up of disparate events across the country. Oh, we had storms in New Mexico, storms in Kansas, and then there's another storm in Maine over this 1 week period. We're going to roll them all up and say severe storms, billion-dollar disaster. One of the problems with the data set is that there's no metadata. We have no idea where the numbers come from, how they're compiled, who makes the estimates using what methodologies. So the mini disasters increased dramatically. One consequence of the mini disasters increasing dramatically is that the loss per disaster in this data set decreased by about 80% over the time period. And I didn't see anybody claiming that climate change was making disasters less costly. So I published my paper, and in parallel, I submitted a request to NOAA to correct it under their correction protocol. After I did that, a whistleblower contacted me and said, if you take a look at this website, which is public but not labeled at all, you can get, at the time, 18 different versions of this data set. And so I was able to download this and do an analysis of how the data set changed over a period of about 4 years. Since it was first established in the 1990s, there's probably been a couple hundred versions. They're lost to time. And when I did so, I found all sorts of changes to the data, irregular inflation adjustments. None of it was documented. None of it could be replicated. So there was a lot of methodological problems. You can read my paper if you want to go into the details. Long story short, it's great for PR, but it doesn't tell us anything about disasters, economics, or especially climate. Meantime, this data set was becoming really important. The NOAA administrator said that this data set indicates that climate change is creating more and more intense extreme events. So going beyond just an economic indicator, it was now a climate indicator. The U.S. Department of Treasury said it explains why we have increasing financial risks due to climate change. I did already talked about the U.S. National Climate Assessment, which led with it as the best data set to show the increasing frequency and severity of extreme events. I don't have it here. The IPCC even included a claim that perhaps NOAA data for weather might be flawed if it doesn't match up with this data set. And then President Biden attributed all 2022 weather and climate-related disasters to climate change, saying that this disaster proves it. So last week, I was supposed to testify before the House Science Committee on this data set. The House Science Committee of Congress was doing an investigation based on my paper. Just a couple days before the hearing, NOAA pulled the plug and said they are no longer going to update the database. They're going to archive it. And I did some digging around. Here's what happened. So NOAA and a lot of the media said, well, Donald Trump killed the data set. I know Donald Trump is no fan of climate change or climate research, but this one has a more mundane story. The fellow, who I'm sure is a wonderful guy, who has overseen the data set for 15 years, took a buyout from NOAA. And when he left, that meant, and this has been shared with me, that NOAA had no in-house capability to continue it. There's no cookbook. There's no methodological details. There's no way that this could be continued. That's if someone who's keeping track of the temperature station at Key West, Florida, retires, the temperature record will go on. Other people can do that. In this case, NOAA lost the capacity to carry it on, and they had no choice but to kill it. And let me be very clear: the U.S. government should account for the costs of disasters. They need some federal agency to help track the cost of disasters, and there's a lot of ways we can track those costs. But it should be economists in charge of economics data, not climatologists. An agency like the Bureau of Economic Analysis would be fantastic, but there are others who could do an excellent job. I see members of the U.S. Congress complaining that NOAA is not doing this anymore. They're the folks who could pass a law that requires another agency to do it. It's not expensive, and you just need the right technical expertise. All right, long story short, the real story going on with respect to disasters in the U.S., if we take all disaster costs, not just $1 billion, and we put them in relation to U.S. GDP, it's flat or declining, as it is in most places, punctuated by some big hurricanes every once in a while. So there's really a good news story here to tell that whether by luck or by good decision making in where we build and what we build, disaster costs have not gone up as you might gather from the $1 billion disaster data set. All right, that's the warm-up. We'll talk about extreme climate scenarios. And this is another one that I and my colleagues, particularly Matt Burgess and Justin Ritchie, have published on a fair bit over the last decade. And I do think it's had some impact. But as you'll see, when we get to the big decisions that the scientific community has to make, maybe not. All right, let me start with this cone. As I'm sure everyone paying attention today knows, climate research emphasizes scenarios, not predictions, because predictions of the long-term future simply aren't possible. One reason for that is that because humans influence the climate system, how the climate evolves in the future depends not just on the physics of the atmosphere, energy flows, and so on, but also what we people do to emit greenhouse gases, change the land surface, put particulates into the atmosphere, all sorts of things, irrigate land. And so we start with some assumptions about how the world will evolve and generate a cone of possibilities for the future. And that's what you see here. The cone is narrow at the beginning. So if each of us asks, where are we going to be 5 minutes from now? You could, if you're drawing a circle on a map, it's going to be pretty close to where you are now. If you say, where am I going to be a year from now? It's going to be a much bigger circle. And so that's what this reflects. You can see there's some different words that we use to talk about scenarios: possible, plausible, business as usual, which is typically taken like, if we keep going in the direction we are, where will we wind up? Probable, preferable. I will get there, but the IPCC formally states that it works with plausible scenarios. It doesn't define plausibility, but that's what it expects to do. So going back in time to the first assessment report of the IPCC, 1990, here's a cone. You see a cone-shaped diagram with business as usual, which was taken to mean here's where we're headed, and then what are called policy scenarios, B, C, and D, for different concentrations of CO2 in the atmosphere. So these cone-shaped diagrams are I'll show you a whole bunch of them, but they're fundamental to understanding the projections that the climate community puts forward. So underlying scenarios are emissions of greenhouse gases and carbon dioxide in particular. And the IPCC explains that an emissions scenario needs to be a plausible representation of the future. The reason for that is that these scenarios are meant to be more than just exploratory objects for scientific research. These are meant to inform policymaking at the global scale and at the national scale, so that they have some connection to the real world. So that's essential. All right, let's flash forward. Around 2005, the IPCC and IPCC related groups decided to usher in a new generation of scenarios. And there's a fascinating story behind all that, but we won't get into that today. And what you see here is another cone-shaped diagram with 1,184 scenarios that ultimately found their way into the AR5 scenario database. You obviously can't do research on 1,184 scenarios. It's too many. So what the IPCC community decided to do was to settle on 4 different scenarios that were quote unquote representative that could be used for all of research. At the time, and this was explicitly stated, if everybody uses the same scenarios, it'll make it much easier for the IPCC to assess the literature. So this was partly shaping an assessment by the design of what the community would use. They were given these names, RCPs, and the numbers refer to the radiative forcing associated with each scenario. That was a fatal mistake because each of these scenarios actually had real names because they came from integrated assessment models. So we had the spaghetti plot, and what I and my colleagues did is we took each of those scenarios and we plotted the 2100 projection of temperature change against the cumulative carbon dioxide emissions from fossil fuels in industry. That's what you see here. So each of these dots is a scenario. You'll see the SSPs which are the newer versions of the RCPs, are highlighted here. And what I did is I drew a red oval around all of them, because by definition, when these were created, the IPCC said they were plausible. All right, so the red oval represents the space of plausibility. So what we did, Justin Ritchie, Matt Burgess, and I did, is we said, all right, it's 2023. We now have a couple decades of actual real-world experience with the growth of emissions. We have the near-term energy outlooks from groups like the IEA, EIA, the oil majors, and so on. And so we asked a simple question. Which of these scenarios survived the test of being compared against the real-world evolution of emissions and the short-term predictions to 2040 or 2050 from the annually updated energy outlooks? And the bottom panel is the subset of scenarios that survived. All of them fall within 2 to 3 degrees by 2100. And the scenarios that are most commonly used in climate research are way off to the upper right. So what we concluded in our paper is that these high-end scenarios are implausible based on what we knew at the time. That could always change in the future. And this is where the space of plausible scenarios are, looking out to the future. So one thing to emphasize. So when the RCPs were originally created, the most extreme one, RCP 8.5, was identified as the business as usual scenario. This is where we were headed. The other 3, the RCP 6.0, 4.5, 2.6 were identified as what are called policy scenarios. This is what happens if we change course. If you go into the history of how these scenarios were developed, originally RCP 4.5, 6.0, and 8.5 were all supposed to be business as usual scenarios. They were all supposed to be plausible futures of where we might be headed in the absence of climate policy. The most commonly used scenario in climate research, by far, the subject of tens of thousands of peer-reviewed paper, is RCP 8.5. The most commonly used scenario in policy settings is RCP 8.5. Even to this day, there are dozens of RCP 8.5 studies being published every day. There are reasons why a climate scientist might want to use an extreme scenario. It helps them in their study to separate signal from noise, of a forced change versus natural variability. I get it. There are legitimate reasons to do that. Today, there are not particularly legitimate reasons in a policy setting to use these extreme scenarios. All right, well, we're at the points. One big problem, we could talk about this with climate research, is that scenarios are only updated about every decade to every 15 years. That means that if you're using RCP 8.5, you're using a scenario that literally was developed in the late 1990s. Imagine if we did economic policy using guidelines from the 1990s. But I digress. All right, so new scenarios are coming. There's a little known group of a couple dozen, mainly Europeans and North Americans, who are deciding the scenarios that will shape climate research for the next 10 to 15 years. They've published a preprint. Again, another cone-shaped diagram. The left panel shows the emissions, and the right panel shows the temperature change by 2100. One of the problems, and I'll get into some of the details, but one of the problems is that these scenarios are being developed with no one asking anything about their plausibility. The RCP 8.5 scenario is not plausible because it projects that the world is going to massively increase coal consumption. And by massively, I mean by a factor of 6 above what it is today. And how things are supposed to work is shown here. The first thing you do when creating scenarios is you start with your socioeconomic assumptions. The IPCC is organized with Working Group 1 as the physical sciences. They probably are the most powerful, but the intellectual start to climate research starts with Working Group 3, with economics and society. And the first thing you would do is you would ask, are the assumptions we're using to generate our scenarios plausible? People can debate and argue about what plausibility means. But what has happened is that with the RCPs, they started in the middle with radiative forcing, and currently they're starting with temperatures. And then they go back to the integrated assessment modelers and say, hey, can you come up with the assumptions that make this possible? Completely backwards to how things should be done. I've identified where the mistake came from. The IPCC AR6 identified this extreme scenario, and I'll point it out in a second, just one notch below the 8.5 scenario, SSP3 7.0 as a current policy scenario. And if we go back to this and we take a look at each of these new scenarios, each represented by a different color in this cone, they correspond to this table, technical summary number 5, table 1 in the IPCC. They are these 5 numbers. They are associated with 4 degree, 3 degree, 2.5, 2, overshoot, and a 1.5 and an overshoot. It's that simple. No one said, well, how many people are there going to be on the planet? What's the economy going to look like? What kind of technologies will we use? It's starting with temperature levels and working backwards. So if we look at where this SSP3 7.0 sits in our plausibility scale, it's here. It's very far removed from anything that could be described as current policies. Now, you don't have to just take it from me. This is from the UN Framework Convention on Climate Change, October 22, projecting out how they foresaw global emissions trending to 2030. Another cone, that's this red slice here. And if you zoom into the fine print, it's below an SSP2 4.5. And to remind you, that's what we called the upper end in our study. So the world is currently trending below that. That's good news. So what does SSP3 7.0 say? Well, it assumes by 2100 there's going to be 13 billion people on the planet, and we're going to build 7,500 new coal plants. Is it plausible? Probably not either of those numbers. In fact, the latest numbers from the UN, which demographers think may be too aggressive, has the population peaking about 2030, 2070, and declining. So that maybe there's 7, 8, 9 billion people in 2100, not 13 billion people. Coal, there's a report last week from Carbon Brief that China's coal may have peaked. Believe it when I see it. But building 7,500 new coal plants worldwide between now and 2100 does not seem particularly plausible now. Here's a global energy mix just about now on the left, and the black part is coal. And here's what SSP3 7.0 has in 2100. Half of our total energy worldwide will come from coal in that scenario. The field is littered, a graveyard full of energy predictions, but I feel pretty comfortable saying that the world's not going to be half powered by coal in 2100. Natural gas, maybe, but not coal. If we also take a look, and this is summarized by Zeke Hausfather, at other projections of future temperature change based on more plausible scenarios. This is the paper I just showed you between 2 and 3. We fit here, and it's nice to see we're in the fat part of the bell curve of our colleagues who have done these studies. These have different assumptions, but the overall consensus of the community is that the world is heading to somewhere between 2 and 3 degrees Celsius by 2100 on our current trajectory, not assuming further decarbonization of the economy, other than what we've seen in the past. There could be surprises. The climate sensitivity could be higher. The world may decarbonize faster. This doesn't take anything off the table, but what it does say is that the most extreme scenarios are implausible based on today, and they probably shouldn't be at the center of our policymaking. All right. So I've gone through these 3 different examples. I think the extreme climate scenarios are the most important. One question which we might ask is, why does a small group of climate experts get to pick the scenarios that will underlie global, national, local policymaking all around the world for the next 10 or 15 years? That seems to be a problem. What is to be done? I wish I had a really good answer for that. I've published on each of these topics in the peer-reviewed literature. It's gotten a lot of attention. Everybody knows my stuff in the climate community. I can tell you, I went to a very high-profile meeting with IPCC people, and the chairman of one of the working groups came out to me. This was a couple years ago, and he said he singled me out and came over to coffee break, and he said, "Hey, I want to tell you that I think your work on RCP 8.5 is spot on." And then he said, "But I can't say that with my IPCC hat on." And for me, that was indication that, yeah, this community has some real problems, that you can't tell the truth when you're wearing an IPCC hat. I'm going to wrap up here in a second, but let me say, I think the IPCC is important. I think scientific assessment is absolutely necessary. There's literally hundreds of thousands of papers published in climate-related fields every year. No one can absorb them all. I don't think AI is quite up to the task yet. But we do need to assess science so we know what's what, what's true, what's not true. And if the field is polluted with literature that does not go corrected, certainly on the timescales of assessment, then we're going to be feeding bad information into decision making, and that's not a recipe for good decision making. I'm easy to find. Here's my contact information. If you haven't signed up to the Honest Broker, you should just log off this right now and sign up. Send it to your friends, family, and then say hi to me when you're on there. So I appreciate it, and I look forward to chatting with you.